So, great, awesome. With that in mind, welcome all of you. I think officially I've got like 17 seconds or something left. And for someone who loves talking as much as me, that shouldn't really be a problem to cover. And yeah, in this sort of American tradition of speeches, I start with a joke, obviously. Cool, great. Well, again, thank you all for coming. This is the first, well, hopefully one of many Melbourne ML Book Club web streaming Q&A. I hope that there's one or two people out there watching this live so that we can see questions from the chat as well. To answer the first question that will obviously, you know, arise from this workshop is no, these t-shirts are not for sale. You have to, yeah. Yeah, so we'll have questions from the audience as well as questions prepared on the slide. And I'll just yeah, kick it off and start with the first question, which is the A3C paper that we read last week compares DQN and actor-critic algorithms. So what's the difference between DQN and A3C, or actor-critic and deep Q networks? Anyone? Do you want to come up here just so that you're on camera, and I'll get the...
I'm not an expert.
This, by all means, and come up and we'll explain it together, or we'll discuss your understanding. That's the... Yeah?
Famous.
Yeah.
A3C focuses on policy, so it'll learn... It's similar to DQ in that it also does require the reward, like, you know, at the end terminal state, but in doing so, it learns the policy as well, like focuses on policy, and it'll use the policy, and then if that policy is better than previous ones and worked out better, then it will use that policy more.
Mm-hmm.
That's kind of like a general thing. That's the main difference. Whereas DQN, yeah, just focuses mainly on what's the next step with the highest reward throughout all of it. Really, I don't think it really uses a policy. But policy in itself is kind of like a learning topic. So yeah. Anyway.
Okay, cool.
Yeah.
Thank you. Anyone's got anything to add, or got major criticism of that explanation, or?
No, I mean.
Do you want to come up and?
No, I agree. So I guess the main thing is DQN is value-based reinforcement learning, where you derive a policy from the value function, and A3C is just a specific implementation of an actor-critic algorithm, which actually is something that updates the policy itself, which is pretty much what he said. I think the main difference between them is the fact that you have an explicit policy. So the actor-critic algorithm is in charge of both how much do I explore and how good am I right now. And in DQN you have to kind of patch that up yourself. So it doesn't really tell you how much to explore, you just have kind of a annealing epsilon that does that. So that's the main difference, sort of conceptually, I think.
Is it fair to say that in this actor-critic the policy is changing all the time and DQN is fixed?
No, not really, but I mean almost. But it's more like the policy, the greedy policy, is really kind of changes sort of very abruptly, because you know if
but the selection is the greedy part is.
Oh, you mean because Q-learning per se is an off-policy algorithm, whereas
actor-critic
all
has to be
actor-critics?
sort of. It has to be, so it's kind of online. So this is, actually that's a very important distinction too. So the DQN algorithm is pretty much off policy, sort of. What you're just doing is you're creating a big cache of transitions. And for each transition you try to kind of learn the value by just doing TD0. or sort of n-step bootstrapping. But with this actor-critic algorithm, you actually you update the policy online, really. Like as you're going, you're updating the policy.
So
Also
with A3C, your policy changes constantly, whereas the
Yeah.
behavioral policy with DQN does not.
Can be very different.
Yeah.
So so Q learning still works even though you're sort of pretty far away from the current policy. But actor critic algorithms don't really work that well. At least not the standard one.
okay, I think that's all.
I think.
Great. So that was already the first success for the Q&A.
So shall I
think?
just stand here until you're
Oh,
back?
no, it's okay. I think as long as there's some noise going through the ether, people will know that this is still live and working. So that's awesome, because that's exactly what I hope we will be doing, that we, in asking a question, we come up with more questions as well as more answers. So the next question is, so in this paper they multiply, there's this logarithm, and they multiply the reward with the loss. What? Why? What's going on?
Reward with the loss.
I think it was in a loss, it's a reward with the grading. Okay, that's
So I think on the last session it was reward was equal like some policy related component times this delta like value related component.
Yeah.
I think that was in reference to implementation. I
Yeah.
think.
Yeah. Right. Okay. Yeah. Gotcha.
But I think the later on I found in a book, I think that's that was the formula to upgrade the theta values.
Yeah.
Theta values.
Yeah, so I guess another way of saying it, I think I didn't explain it very well then, but the expectation value of the TD error is exactly what the advantage function represents. So if you take many observations of the TD error, that is the advantage function.
Is that for regularization as well?
No, I mean I
Do
think
they do that for regularization?
So I think, I mean, it's hard to discuss something that we don't really have on the screen right now. But basically, the loss function is sort of the empirical expectation of the log of the policy times the TD error. So it's not really actually here. So there's not much for regularization. So you can do regularization as well. In this context, that means that you want the policy to be not too far removed from a uniform policy, basically randomly sampling. And the way to establish that is you can basically introduce an entropy term in your loss function. Yeah.
Cool. Yeah. Awesome. Thank you. Right. Next. The A3C paper mentions LSTMs used with the model. Is the advantage in A3C the same thing as attention in RNNs and NLP?
No.
That's a straightforward answer.
That's just a different.
Patrick seems to.
I don't really know what attention mechanism is. So could someone explain that?
Yeah. So the
other Patrick, maybe?
Oh.
Yeah. So attention is the idea that you compute how much. The idea is that you want to take a weighted average over various bits of your context. So, like, when you have a sentence, you might take a weighted average over all the different words in the sentence to pay attention to. So this isn't adding up all the vectors, it's adding up, well, you want to multiply these vectors, these sort of word vectors, by some sort of weighting based on how relevant they are. So like when you read a sentence like the A3C paper mentions LSTMs used with the model, I might pay attention to like A3C and LSTM and model, but not that much attention to the word the in order to understand it. So that's advantage, but I think that LSTMs aren't the same, don't necessarily have anything to do with attention. Like LSTMs and attention are two totally different mechanisms. You might use one with the other, but you don't have to.
No, I agree. So just to add, I think well basically is this? Oh yeah, this is on. So there are three concepts here that are pretty much unrelated. So one is LSTMs, the other is an attention mechanism, and the other thing is advantage. So advantage is just a value function, basically. Just think of it as the sort of the zero-scaled version of Q. That's all that advantage is. There's nothing more to it. So that's it. It's just a Q function, basically. Attention is just a way to use global information rather than just only looking at local patches. So you can either take it in a sentence where you just kind of focus on both this word and this word, even though they're far apart. The attention mechanism allows you to do that. And then LSTMs is just a very specific.
So I think I saw somewhere a good example for attention is when you're doing translation and in different languages, I don't know, let's say the verb and the noun have different positions, so
Yeah.
are described by two words, and this is where the attention comes.
Yeah, exactly. So it's particularly useful if you have not only a rich input but also a rich output. So then you have for each, especially in machine translation, like let's say you have two different languages, then the ordering of the words could be jumbled depending on what language you're translating. Anyway, and LSTMs is just a very particular recurrent neural net cell. That's just it. I think that's
Well, we had someone ask, and honestly ask, like, I don't know what that is, what does that mean? Instead of just, sitting there and staring. So I'm very happy. Thank you, Patrick. Cool. And the A3C model used LSTMs with RMS prop, which I've recently learned is actually not the hippest, the best thing since sliced bread anymore. But in general, which neural network architectures would you use with reinforcement learning, and why? Like, for example, LSTMs, as I wouldn't have necessarily thought that that's a good idea, because they're so sequential, and at the same time they're quite limited. When you have a random walk, they completely and utterly fail. So it's I was looking at that going, what other network would I use, and how would, because in supervised and unsupervised learning we're quite comfortable with model selection. We know when and when not to use fully connected versus convolutional and so on. But why would I prefer an RNN over a convolutional neural network in my reinforcement learning problem? Yeah. Do we have any theories or any questions on that?
I think the DAM asked.
Finally.
I think not very constructing answer is the ones that work, and I think no, but I think that with this paper that we discussed last week, I think we saw this evolution of those algorithms, and I think my feeling is that deep Q learning got some prominence early because I think that was the one of the algorithms that could be implemented basically using the neural networks, and this workaround with the having two networks and the slow update of the target network, and this concept of the experience replay. So those were, I think, some things that were dictated by just the fact that the network couldn't be trained, and the paper that we discussed last week with this. Which again, I think it stems from the fact that initially the concept was to actually implement the distributed neural network training. So that was this distributed gradients calculation. And I think then it was adopted to this reinforcement learning setting. And that's why in that paper we saw that other algorithms, the own policy ones, the SASAs and alike, where they could be used actually in a reinforcement learning setting.
Did they use LSTMs for those? I don't remember off the top of my head which neural network architectures were used for the other models. I only remember that A3C had LSTMs.
So that's just a standard CNN. So they, I think. So this is where my. So I don't know the details of the A3C. That's the disclaimer. What you have to do in DQN is you basically have to stack, say, a certain number of frames in order to get sort of fully observe the state. So the state is not just the screen that you get to see right now, but it's also the speed at which things are moving on the screen. So you have the position and the velocity in terms of sort of physics language. So you need more than just one frame. I thought, but I might be wrong, but I thought that you use LSTMs to basically patch that up. So that you don't say, I'm taking 4 frames, you're just saying, you're just taking frame by frame by frame, but the LSTM is sort of clever enough to remember parts of the state from the previous frames. So that, yeah, I think...
so it kind of has like a sequence, like of like, so it puts like the input from... So, should I go?
Well, it's not just for us here, it's for the millions out there.
I'm not
Your children who will one day...
Not 100% sure, but I believe LSTM sort of focuses on sequences. So instead of each input being just standalone, it will pass each, in the neurons, you could say, the previous input into the next one, so that the value of the next input requires the value of the previous input. So it's all affecting in a sequence, basically, the next outputs. And I think, were we talking about CNNs before? I can't. What was the question?
I think you said DQN was using CNNs. Yeah.
That's what they do in the DQN.
Oh no, that's just more the sequence part of the LSTM, I think. But I'm not sure with DQN. With the images, I know it's good with CNN. I guess you already know uses the kernels. It's good for images using a CNN. RNN is good for videos. I think it's just because it's lots of frames and it's really good with memory. But I think with when it's like a simple image, like in games like board games, you don't have a lot of images. So it's just when you move the piece, then it's like a new image, but it's not many. So you can use a CNN because it's simpler. Yeah, I'm not sure if there's any more questions on that. But, yeah.
Okay, great. Yeah, any more comments or questions with regards to that?
RMS Pro?
Well, yeah, as far as...
used it because Adam wasn't around then.
Yeah.
I think that's the only thing.
Probably, yeah. Would anyone use anything other than Adam for a neural network to train?
Sometimes I just use like plain old like momentum, and it sometimes outperforms. Just because of its. Yeah, I mean, or with or without Nestor, it's just because it's more robust, because it's simpler.
Yeah, true.
So yeah, sometimes I mean I don't even know. Forget about the because. I sometimes do just momentum and it works better.
Okay. Fair enough. So there's still some magic in there. So yeah, that's a thing that if you look at all those, modern, if you want to call it, like, or like recent, right, reinforcement learning problem solutions and so on. Everyone's doing some kind of policy, something or other. PPO, PPO2. Are they just better? Is that just the thing? Should you just use policy gradients on everything? Like program your Roomba with policy gradients? And it's just... well, maybe Andrew... Oh, okay.
I would say no. Actually, so Q-learning sometimes outperforms because it's better at off policy. So it's just not true that policy gradients is always better.
And both Patricks.
Wouldn't you want to use the value if you could, but sometimes it's very difficult or just computationally impossible to actually compute the value for all the actions that you could take. So you have to use the policy instead. Isn't that?
From my understanding, I know like 2 cases where you would choose policy over value-based. In games like chess or Go, you don't know if the next move is going to be good or not, where you can pinpoint a value for each step. So since you don't have the values, you can use a policy behavior, or you start off randomly with some random behavior or policy and then play it through. And if it wins, then keep that policy. If it doesn't, don't use that policy. But in certain games where each step you get a reward, then value-based might be better because you know how to set up the rewards and then you just use the values. You don't have to worry about a behavior which, because it's kind of more certain, I guess. It's, what do you call it? It's just quick, it's constant, yeah. So.
Yeah, like policy is much slower to do because you don't take that big greedy step each time, but you can actually make it more stable because it only takes small steps by going down that gradient, basically. Is that wrong? Is that true?
I don't know. I think
Yes, sir.
All I was going to say is, just trying to find a problem you're trying to solve firstly. Just do that. In examples you mentioned with Go, I mean, that's Monte Carlo tree search. That's kind of what it's using, that's how it's solved Go. And then they moved on to more policy-based methods with AlphaStar, which was used for StarCraft. In terms of, I think, the point you were raising earlier, it depends what problem you're trying to solve. That really is. You can look at a classic game such as TD Backgammon, and that used a very simple neural network, which solved the problem. That is, by solving the problem means it became a perfect game. And then when the actual neural network was increased, that is from a value-based perspective, it actually became much better in terms of from a performance perspective. So it all depends on what you're trying to solve and what sort of performance you're trying to get.
I think, I agree. I think one more thing to add is that policy-based methods have this sort of bottleneck, which comes from the fact that the policy gradients, only make sense at the current point. So where the policy is right now, or somewhere close, that's where the policy gradients make sense. And if you're somehow removed from there, you have to throw away your data. This is exactly what the problem is with policy-based methods. And there are ways to solve it, but not completely. But for value-based methods, you can completely recycle any observation that you have. So I think that's the main difference between those two.
So kind of my read on all this is that I guess I have 2 opinions here. I think that policy gradients are probably used more often because of sort of the nature of the reward system. Is like there's sort of temporal difference stuff. Like just looking at the next step may not be as good as looking at a more rollout-based approach, where policy gradients fit in more nicely. I think what Chris is getting at is that sometimes you have sometimes it's easy to sample from your environment, and sometimes it's difficult. In a video game, it's really easy to sample from your environment. Mm-hmm. But if we're talking like, say, robotics, where you actually have to do something in the real world to gather data, then it's value-based methods may have an advantage there because they can use that data more effectively.
This is really cool because a lot of these questions are from Quora, so maybe I should just run a, what's it called, like a subtitle algorithm over our recording and then just post whatever comes out to Quora. Okay. Yeah, I also think, and I might misremember this one, but I think another aspect here is like if you have really bad sort of spaces, state spaces for value-based methods, yeah, you would just naturally go to a policy gradient one, because it could just be that even if you have discrete spaces, if these discretizations are so different that you have like really asymmetric sort of distributions and so on, then it could just very well be that policy makes a lot more sense because you never explore your state space fully otherwise, that sort of thing. Or if you have a full-on continuous state space and everything just becomes more infinite than infinite, then you just might be better off this way. I think I remember that correctly, I hope. Right, so policy gradients and policy search is the same thing, right? Or not?
That's kind of the thing. Sorry, I keep talking about. Anyway, so I think that at least I might be wrong, but the way I see policy-based methods, they're basically they do two things. They figure out what is the best action to take, but they also say how much to still explore. In sort of statistics or sort of normal distribution, say, they're calculating both the mean and the variance, the uncertainty as well as the expectation value. And by which what I'm trying to say is that because if you don't just learn the expectation value, you also learn the uncertainty, is that it also that gives you the amount by which you still need to explore, basically.
Anyone got any comments on that?
Write it down.
So to me, this kind of gets to the difference between AI and machine learning, or machine learning and deep learning. That AI solves search problems, and what deep learning does is use a particular search algorithm, namely gradient descent, with various bells and whistles attached. So I think policy search is, let's look for a policy. Let's look for a procedure that, given a state, will yield an action, or a probability distribution over actions. Whereas policy gradients are, all right, here's one particular method that we can use to find the best policy. Another policy search algorithm might be genetic algorithms, for instance. That's a gradient-free method that you could use. Probably you did use back in the 90s when nobody did deep learning. But I think policy gradients are kind of the dominant policy search method today.
Mm-hmm.
Yeah.
Anyone felt like you had any? Oh, okay. Trying to encourage people to voice their opinions. Right. So I'm so glad you started talking about evolutionary methods. That was not planned, but so what was that you said again about the difference between policy gradients?
And look, I think honestly there's less of a difference. So let's just talk about. I'm gonna ignore the word policy in this question just for the hell of it. But gradient methods in general involve this idea that we have this continuous search space, and what we're going to do is find some kind of error term and do essentially hill climbing. Essentially, we want to nudge our thing towards a better state based on some kind of error. Whereas what evolutionary methods do is we say, all right, well, we have some kind of encoding of our space, and we have some sort of fitness function that we care about. Say the cumulative reward for an episode. And evolutionary algorithms search the space not through gradient methods, but through this technique called crossover, which is analogical to the biological concept of sex.
Mm-hmm. So, sorry, can you just rewind a little bit? Because the fitness function can include the reward, but obviously the reward is not a fitness function. So can you elaborate?
Yeah,
a bit
sure.
more?
So in reinforcement learning, our fitness function would be the return, but that is the sum of all rewards. But in general, fitness functions are sort of user specified, right? Like the fitness function should be whatever you want to optimize for.
So, because I remember looking when I looked at this is sort of a, I guess, mean of several questions that I came across on Quora, and one of them asked about sort of what the difference is between reward and fitness function, and I looked at it and went like, reward isn't really a function to start with, so I didn't really understand what they meant, and then people in the answers tried to explain that the reward is known and the fitness function is not known, and I kind of understand what they mean because you as an agent, you don't get involved in this fitness function kind of thing. But with respect to the reward as part of the fitness function, you can perfectly well include known variables or known events in the space as part of the fitness function. You just don't have any, you don't get to select or influence the fitness function. Is that a good way, better way to look at it? Or
Yeah, I mean, what I'd say is like the reward is data that comes in as a result of your process. And your fitness function is a function. That is, it's a way of taking a policy or a set of parameters or a doodad and outputting a number. And, you know, they're related in that you probably want to use rewards to compute your fitness function when we do reinforcement learning. You may not. I mean, I'm trying to think of a case where you wouldn't. Maybe some of this, even then. I mean, you could incorporate non-reward information, potentially. You could incorporate stuff like speed or sparsity in your policy, maybe, just as a way those things could differ. But yeah, obviously, if the goal is to maximize reward, we want to include reward in our fitness function. But yeah, the key to understanding the difference, I think, is function. Rewards exist on their own. Rewards exist as data that we sample from our environment by taking actions. Whereas a function takes a policy, does some stuff, and returns a number.
Okay.
Maybe to paraphrase,
Yeah.
or to kind of follow a question.
Could you?
Why would we prefer one over the other?
Oh.
Well,
While you answer that, I will check whether we've got questions in the YouTube chat.
Sure.
So.
Yeah, sure. So I think one reason to prefer, so why prefer policy gradients or evolutionary algorithms, I think is the question. So I guess there's one answer I could give there is that I think policy gradient methods are nice because they fit kind of more nicely within the deep learning type framework. We have all the advantages of deep learning. We have the big representation capacity, and we have efficient numerical methods to actually run through lots and lots of iterations, where, you know, gradients run on GPUs, everything else runs on CPUs.
So would it be possible to take the way I mean, I guess this is a more general discussion, but so I always looked at the gradient methods as they work so well because they're cheap, not because they're particularly sort of close to reality, because usually the optimization, the how do you call it, the loss surface is definitely not smooth enough. So basically, it's a non-convex problem, but we still use it because we can take so many samples at once, because calculating the gradient once just gives you the number of observations is equal to the number of parameters that you need to update, so it's really nice. With evolutionary, like genetic algorithms and that sort of stuff, I always thought that you need to do a lot more iterations, so it's more expensive. Is it?
Yeah, and I think that's right. So gradients are a lot cheaper to get. I think also you have calculus on your side when you do gradient methods. You can prove stuff about convergence and whatnot. The thing I like about, so I guess the pro side for evolution is you don't care about smoothness anymore. You can cram whatever kind of complexity you want into that genome. So one thing I think is actually very, at least from the papers I read, one thing is that's common is that you do policy gradient methods in your inner loop and evolutionary algorithms in your outer loop. So you would decide things like your network architecture or your, you know, the...
Where you don't have locality or smoothness or...
Yeah, all the fiddly hyperparameter stuff you would do
So you
using
call
evolution.
it hyperparameter breeding?
Yeah.
Interesting. So that comes back to what we talked about, I think, on Monday. That was it? I can't remember. Was it Monday? That in the end, like, you can't really go faster than random, and it's because evolutionary optimization is more or less similar to random search to some degree, right? There's an element of randomization.
Yeah, there's an element. I mean, ideally, it's hopefully it's not just random, but
They have with evolutionary, it's basically the same thing as natural selection, where like they'll even place a random mutation. So combine two, the fittest ones usually together, and not necessarily the best one only. And then every now, well, each, I think evolution, they'll have a random mutation, so it'll allow more randomness. Like it's sort of like having temperature where you allow some randomness, so which might improve it, but not certain. But
So when you, maybe I'm anthropomorphizing too much here, but you reckon we are automatically including a somewhat already evolved mechanism in this evolution, where basically like two algorithms meet and then the other one goes, oh, what's an algorithm like you doing at an address like this, right? And then they exchange.
yeah, they kind of maybe like for example with let's say you're just finding which set of, like if you have which set of 8 numbers perform something best,
Yeah.
and then you might have 2 sets that do it kind of well. Then you split them maybe down the middle, or kind of randomly somewhere along the set, like maybe a third of this set in the.
So it is more a kind of breeding. It is not just random evolution. There is you really try to breed the fittest and exclude the ones.
The lowest, I think the lowest ones they still breed some, but they breed less, and the top ones will kind of mix more together, and then they'll survive more, and then
So maybe there's somewhere between hyperparameter breeding and hyperparameter shepherding.
It kind of I mean it could be for parameters, it could be for anything really. That's why I guess it's pretty flexible with what you want it to be used for. But
Cool.
as you said, the fitness function can be kind of tough sometimes. So.
Cheers. Okay, so we've been talking about experience replay and before, and this sort of pool of these samples and where to sample from and what to sample from. I guess this is a question that I badly paraphrased, because there's more or less 2 questions, right? One of these questions is, do I need it? And the other, do I need it like at all? And the other question is, when? And is it necessary in some cases, or is it always optional, or are there, like, to what degree would I want to or not want to use experience replay?
It's a reduce variance. It's a trick to reduce variance.
But you would always, so when you can, you would use it, or how would you?
So, I think in the DQN paper. Sorry that I keep talking about that, but I guess this is where that comes from. So they say they use it because very often when you do something like Atari, you get states that look very much the same. But may have a very different amount of expected reward that you get from them. So just to reduce the variance of your training data, you use experience replay. So
Mhm.
basically what you're doing is you're just storing all of the transitions that you've seen in the past in such a way that, you just kind of reduce variance. So the whole point of DQN and experience replay is to make reinforcement learning look more like supervised learning. That's the whole idea.
Mhm. Andrew, I think, has something to say about that as well.
Yeah. I'll just probably add to that. I mean, what Vladimir Mead did in his paper, the DQN paper, he really what he had, it was the Atari game, so it was an 8-bit game, so they had all the different frames coming in, and they needed to use experience replay in that respect, so they can understand with the frames of these games. And it really was to the point of actually trying to turn it into a supervised learning problem, so they actually understood the state space and they defined the optimal policy. Then the next step from that became double DQNs and then rainbow policy. So that's just an improvement onto the DQN algorithm. And then if you look at robotics, there's a hindsight experience replay, which is HTR, and that actually takes it to the next step. So you can utilise that with robotics. So you can get your optimal policy to find. So you can understand the state space to find the optimal policy, and that's the next step.
Mm-hmm. Patrick?
So obviously, if you can push RL more towards supervised learning by using experience replay, when would you never want to not use it?
So for cardball, you don't need it. Like if you have an environment that's just very small, you just don't really need it, basically. Yeah, especially when your input space is very rich, basically.
The key is just like state space, and then also that comes down to exploration as well. If you understand state space, you see state space, you don't need to explore and define what policy.
Can you?
It was just a comment. That's all. Yeah.
So just to sum this up, if I understood this correctly, like in noughts and crosses or tic-tac-toe for our American viewers, you would not use experience replay. You would just, the state space is, what is it, like 397 states or something like that. It's not worth it. Yeah. Or for a small game like backgammon, you probably wouldn't.
Backgammon was 10 to 20. I mean, but the thing is, you didn't need to use it. You just needed a small recurrent. Restore your.
Yeah, that one totally worked.
Yeah, you know what? You know why that works? It's because there's randomness from the actual game itself.
Yep.
Sorry. The reason why you didn't need to do that for TD backgammon or TD gammon, I think, is because there was enough randomness in the game itself because of the dice that actually that sort of got rid of most of the variance there. Or yeah.
Yeah, and the key thing is stochasticity, and that's if you've got stochasticity, if you understand your state space, you don't necessarily need it, and that's really the key thing you look for.
That's great. I hadn't actually thought of that. That, of course, like the unlike chess or checkers or whatever, or tic-tac-toe, you have this huge element of randomness in backgammon that you don't have in those other games, which of course increases increases your state space, and sort of would you say that is discontinuous, or how would you say that? What's the right way of thinking about that? The state space is not discontinuous. That's not the right word.
No, it's more the way you sample the next state.
Yeah, yeah. So it's almost like the game itself is like experience replay drawing from random states.
Yeah, so you explore enough just by having different dice.
Yeah,
outcomes.
yeah.
That's
Mm-hmm. So it has a built-in epsilon.
Yes, exactly.
Yeah. Mm-hmm. It's interesting. The environment has a built-in epsilon, not the agent.
Yeah, and that's a coincidence.
Yeah.
Which is
But
lovely.
that's a very important concept when you actually
Yeah.
go further down the track.
So, are there other examples of environments or things that you can think of that have elements like this? But pretty much any game that involves dice, I suppose. Like if you were to play, well, Dungeons and Dragons doesn't really count because that's very, very hard to play. I
Poker.
imagine as a poker is
Poker is complicated because you're actually playing against, but
it's
there's
not
also
dice.
randomness there.
That's right.
Yeah. Or
Yeah.
I mean, I guess there's blackjack, which is just one of the gym environments that you can play with. There's some randomness in there.
Yeah, and it has an optimal strategy, right? Blackjack does it?
I guess so.
If it's two-player games, yes, it does. You do.
So as long as it's 2 players, there is. But if it's more than 2 players, there's no longer.
That's multi-agent. That's a different problem.
Ah, interesting.
So because because effectively what we're talking about is perfect games and imperfect games, and whether it's a 2-player game
Yeah.
or not, or
Yeah.
it's a multi-agent game, but all of which have been solved. All these problems have been solved. And if you do actually break it down into that, you realise that okay, I've got a perfect game space, I've got an imperfect game space. Is it a 2-player game? Is it a multi-agent game? And then the best example of the multi-agent game was, well, there's been 2 really great examples. Once was the Doha, which was a really good one. So which is 5. You can have 5 players in that, and there was a wonderful competition over last weekend, I think it was, with Greg Brockman and Ilya Sakseva. They're winning in the esport game, so that was a wonderful example. And prior to that, the other example being with what DeepMind did with StarCraft, which is one of those another multi-agent games, which they have actually solved, which I think is quite exciting.
Cool. Yeah, that's really interesting. I hadn't thought about it in that way. I guess I haven't played backgammon in a long time. So there are a lot of people that talk about this, like some have like Venn diagrams which overlap like very little and stuff like that. It's that supervised and unsupervised learning are not the same. But we've already mentioned this like a little bit, where you said that when you use experience replay, we want to sort of try and make our reinforcement learning problem more like a supervised learning problem. Could you take any supervised learning problem and just transform it into a reinforcement learning problem? And how would you do that, and when would you do it? Is there a use in that, in doing that?
Well, it's sort of been proven. They've already done it. So if we break it into supervised and unsupervised, so in terms of the current challenges that remains in reinforcement learning, it's unsupervised learning problems. They're the current challenges that remain that need to get addressed. In terms of anything supervised, that's already been done with value networks and policy networks and breaking it down and using the simple example of Atari. So that problem was solved in about 2015 in terms of turning something into a supervised learning problem, solving that, and then moving on. So the real challenge now is looking at
supervised learning is solved? What are you saying?
yeah, from a reinforcement. Oh, sorry. In terms of reinforcement learning, yeah.
So are you basically saying there is a supervised reinforcement learning and an unsupervised reinforcement learning?
Yes.
How would you distinguish those? That's interesting. Okay, I didn't see that coming. How do you distinguish those? And how, to what level do you think the supervised ones are solved? Because I mean, Montezuma's, I still feel like they cheated, because the way they solved it was they showed the computer and then it figured it out on its own after one demonstration.
No, Are we talking about imitation learning, or are we talking about actual, like, what usually people mean by supervised and unsupervised?
That's what I thought we were talking about. Is what people usually refer to what supervised and unsupervised is. Yeah.
I thought we were talking about supervised as in like the traditional data science supervised. So
That's what
I mean. Yeah.
So how would you, can you just roll that back for me? How would you classify the supervised and unsupervised versions of reinforcement learning, where you mean?
Oh, okay. So with the I thought with the Atari 2600 game, so they turned the first slide into a supervised learning problem in order to solve it, and that was with the DQN algorithm, and that was the first one. But the next challenge that I'm saying what's not been solved is the unsupervised learning problem, and that's what the focus is now.
So you would say that if you wanted to solve I'm trying to come back to another question that we've seen. If you wanted to solve would that be one of those cases where you would distinguish between maybe using value-based and policy-based methods? So for an unsupervised problem, you would use a policy-based method rather than a value-based method, and for a supervised problem, you would use. So is the supervised, does the supervision sort of analogy come in with, like, when you have a problem that you can assign a value to, so to speak, where you have a when you have a possible I guess deterministic value, or
I think you're trying to look for a reward. If the reward's known, is that what you're trying to look for, as for your analogy?
I'm still trying to. I think
Sorry,
it works for me as an analogy, but
I wanted to take the terms, pull the terms apart.
Yeah.
So supervised learning, unsupervised learning. That's just standard IID sampling. Let's call it that.
Mhm.
There's a data set and it's sitting on a Kaggle server somewhere. It either has labels or it doesn't. If it has labels, we call it supervised learning. If it doesn't, it's unsupervised learning. That's what
Fair enough.
that's the definition I
Mhm.
like.
Yep.
Reinforcement learning is something very different in the sense that your observations are, first of all, not IID. Plus, you need to figure out what to do in order to explore the different spaces and the distributions of your observations. Very different problem, completely different. Now, in order to solve reinforcement learning, we try to take a hard problem and sort of pull it towards the known. The known in this case is to try to make it look as much like supervised learning as possible, which is all this DQN business. So I agree with that. The other way around actually is pretty cool as well. You can do that too. So that's his learning to predict thing. So that's Rich Sutton from like 1980 or whatever, where he does the other way around. So he does supervised learning on a like ordinary, maybe IID, but not even necessarily, set of observations, and you just learn to predict the next value, basically. So it's kind of a precursor to online learning in that regard. Right. So that's the other way around. If you're saying unsupervised learning, they're working on it, but they're not very far with I have no idea what that means. Like I don't know.
No, that's fine, because I mean, that's paraphrased what I was saying. In terms of unsupervised learning, I don't think it's been resolved. Turning a problem into a supervised learning problem has been resolved, and that's what the big challenge is now, to try and solve that.
But it's not exactly unsupervised either. Like so, right? Sorry.
Or that.
So I think, well, I'll follow on from that first, following what you guys first said. I think what you're referring to is supervised reinforcement learning is at the beginning you could say, oh, these are the values at each step, and then, but that's manual, it's supervised. Is that right? Yeah, so you're supervising it because at each step you're kind of helping it. But in more what's happening now with, I guess, AlphaStar and everything, it's more unsupervised. Well, I actually used human data at the beginning, actually, so I'm wrong there. But with Go, for example, it's not supervised. It kind of just does its own thing, and then it determines what's good or what's not. I guess that's what you mean by unsupervised. Is that? Okay. Okay. I'm not. Yes. Is that?
Because you know what you're trying to achieve.
Okay. So. Yeah. So in that sense, it's still supervised. Like the terminal win or loss is still like supervised. Like so it knows when it. Yeah. So you're saying like. Okay. Oh, like truly unsupervised. So it doesn't even. It even learns like when it's won and when it's lost. Like it would learn that the game's ended and I had more something, and it would learn.
Yeah. I'm trying to think of a better example. I mean, because I think the biggest challenges now is, off the top of my head, I think the biggest challenges now is any sort of scientific problem. Those sorts of things where, which is, even having said that, I mean, the protein folding problem was solved. Now, I think, yeah, I'll say that. Like scientific problems like protein folding and those sorts of things.
So I remember reading about attempts at starting a reinforcement learning problem that didn't have a specific reward function, that was trying to determine its own reward function. I can't remember what that was called, like, or curiosity functions, things like that.
Yeah.
I could imagine you could consider that, I suppose, like unsupervised, because you don't, with supervised, I feel like if I put a label on something, yeah, if I have my pile of 2 photos and one of them, or like if I have a pile of photos and I know there's like cats in there and dogs, then my unsupervised training would just be I end up with 2 piles of photos.
Yeah,
and my supervised learning would be I end up with a pile of cats and a pile of dogs. Yeah.
Can it be somehow paraphrased as...
Can you pass the microphone to please?
Can it be somehow paraphrased as the supervised reinforcement learning would be trying to find the answer to the question, and the other one would be trying to ask the questions?
Yeah, I was thinking along a similar line, where if you have a reward, if you've defined a reward function, then that's a supervised-ish approach, right? If you, like my standard example is always the Roomba that just zooms through your house and tries to, I don't know, if it gets a negative reward at each time step, then it tries to save battery or something like that. You tell it what the goal is. And if it doesn't, then I guess, yeah, that would be an unsupervised like approach when you say, okay, yeah, I don't know what to look out for in this environment.
There's one more question. I think also with this question, maybe like he's more referring to like cat, is it a cat or not, like image sort of decision. So I guess in reinforcement learning, you would give it the state is the image, and then an action would be the choosing of it. Whereas in a normal image recognition, there would be no like state or action, no markup decision process. It'd be more like, that's why I think maybe there's an input and is it right or wrong with the classification logistic. So I think that's how you might change. You would turn it into a markup decision process with a state and action and reward.
Yeah.
So in that sense,
Wouldn't be the confidence what the picture is similar to this probability in a markup?
The reward would be kind of be the same thing, but it's just sort of just making it reinforcement learning with adding the markup. I mean, I don't really know. I guess you don't really necessarily need a MDP, but I'm just thinking maybe to make it more RL than a standard.
Oh, you mean
supervised.
sort of make the reward like 1 minus the loss or something along those lines? Have a version where you can increase the reward when your loss gets lower, sort of thing?
Well, because in supervised learning, if you just run it through a standard linear regression, it's just the input, and then you have to, what if it's classification logistic function, and if it's right or wrong, feed it back. But in reinforcement learning, you have the mathematical framework of a state and an action and all those sort of things, which aren't included in a normal supervised machine learning sort of. So anyway, that's
Could you imagine, or the other way around, looking at it the other way around? I'm doing this amazing Coursera course at the moment called Practical Reinforcement Learning, and it's run by this Russian university. And the guys I wonder how they came to reinforcement learning, because they've got some really interesting examples and a really interesting sense of humor when they go about this. That's where the if you don't know the probabilities, what you're going to do slide came from. And and so one of the examples that the instructor there gave was this robot that's trying to walk, and if you don't put the right reward function on, it'll learn to fall down, because it might get rewarded for falling down. Yeah, if like it was about like discounting properly and rewarding properly and so on. And so I wonder if there's a way that you could think of a problem where you end up with a like, would the robot learn to walk if it didn't have a proper reward function? If it had this kind of, if there was a way to,
it's kind of like
if there was a way to phrase the problem as a find the reward function first and then learn, could the robot still learn to walk?
It's kind of, there's this really famous quote from Alice, I think Alice in Wonderland. It's like when the girl asks for directions from the cat's like, oh, well, where do you want to go? And she's like, well, I don't know. Then the cat's like, well, anywhere is good. Anyway, like, and then it doesn't matter. Then it doesn't matter which. But so there has to, I think, in a sense, there has to be kind of a goal somewhere so that so it can go towards it. Anyway, this is getting interesting.
Thanks. Okay, so this is exactly where I wanted to kind of chime in. So I guess the way to look at unsupervised learning is usually it's something like reducing variance, right? So you just create small enough chunks so that those chunks together, the variance of the parts is smaller than the variance of the whole thing. That's usually what people.
So there's more certainty, so you can get to the
So another way of saying that is that there is a goal to unsupervised learning, even though we don't have the whys, the labels, but we still have the actual sort of objective, and the objective is to reduce variance in our data set, basically. I guess if we need to really answer this question, I think the answer would be the IID-ness, or sort of the fixedness of your data set. That's in supervised and unsupervised alike. RL is very different in the way that it determines what you observe. So that's how they're very different. But you could imagine turning an unsupervised problem into an RL problem, and supervised as well. So that's pretty straightforward. The other way around is sort of, I guess, DQN and that sort of thing, where they try to make it look more like supervised learning, because supervised learning is a thing that we know how to do. Why you would want to turn an RL problem into unsupervised learning makes very little sense to me.
Oh, well, very interesting question. I think Andrew still has something. Yeah.
just want to clarify something with regards to the protein folding problem. That was actually solved. I've just remembered that now. I think I said earlier it was still left unsolved, but it was actually solved. It was a problem that was being solved by DeepMind. But yeah, I mean, exactly how it was summed up, how I was going to say it then. Yeah, that's all I guess I really wanted to say. But yeah, those are the biggest challenges facing everybody now, is those type of challenges, particularly in reinforcement learning.
Cool. Okay. Right. So interesting that you spoke about variances before. Like this. I literally did not plan this. It's awesome that we come across these topics. Policy gradients. That is a question that I more or less copied from Quora. I think 1-to-1. Policy gradients have high variance. Why? And interesting. Okay. Someone's moving furniture upstairs. Why is that, and what do you do about it? And one of the things that we've spoken about is we try experience replay, but does that always work? Yeah, and
it doesn't for policy gradient.
So what do you do then? Yeah. Let's go to.
I have the second thoughts on the experience replay.
Oh.
So actually, is the experience replay to separate the samples in a state space or in a time space? So.
Sorry.
I don't understand what you mean, because if we've got markup decision process, I mean, obviously it's time variable.
Yeah, but
Variance in the time direction or variance in the...
So I think you earlier said that the sometimes the states are similar and they have different values. So it would be like let's say on a like a 2D space, they will be like close to each other and they have different values. So the purpose of this experience replay, is it to separate those when the networks are updated, or is it to, if we have on a time scale and we just move through the states, is it to separate them like in that first case that when they are close to each other in a state space and the values are different, or is it to separate them in a time space? So not to do the updates of the states from the states that are coming from the time that is following one another.
I'm not quite sure how to answer, but I think so. The example that they give in the kind of variance that you need to sort of work with or fix is the kind of variance. The example that they would give is you have let's say you're playing an Atari game and you shoot a spaceship, and so the state right before the laser beam hits the thing and just after it, the state space looks very, very similar, but the amount of reward is suddenly changed a lot, and it's that kind of variance that you need to kind of smooth out.
So it looks like it's both.
Yeah.
Could you bin state spaces like that, or would there be? What would be a good way of addressing that? Because I've been working on a binning sort of discretization problem like that, and I'm wondering sort of what options I have. I've started looking into this. Patrick suggested looking into AIC for this sort of thing. Is there a way that you could apply this to state spaces, or is it because you don't have enough information about the distribution? Would you have to sample a lot, and then afterwards? It's a I can't remember what it key information criterion. Yeah.
But I don't understand why you use that evaluation metric, unless I've missed something.
For optimal binning, yeah, that's what I haven't had too much time to look into it yet. I literally just started looking at it today. But it was one of those things where I wonder if there's something like that you could do with state spaces where you could bin them and you wouldn't necessarily have to bin them regularly, but you could bin them in like by a different distribution. Whether there's something whether you could kind of save there, and maybe apply not just DQN or something like that, but in general just have a different sort of a kind of pre-processing, I guess, approach to your state space or to your input there. I'm not sure if that. Yeah, I'll have to look into that. That will be.
I think with a lot of this, I'm not sure if I'm answering right, but with a lot of this, the feature engineering or the pre-processing is kind of, you want that to be part of the learning process. Very often it's just basically just learn a couple of convolutions.
Yeah.
So the high variance in policy gradients has to. The high variance in policy gradients has to do with the fact that the signal that you get. So let's take just plain vanilla policy gradients. So actor critic. So the signal that you're kind of fitting on is the TD error, and that just has a lot of variance. And what can happen is that you're sort of overfitting on just a couple of values that just happen to turn out a certain way. And then on top of that, if you don't regularize your policy, you're just going to completely overfit, and you're going to, like, the endpoint of the optimization program is basically a greedy policy, which is sort of high variance in the space of
so you just end up
actions.
on some local maximum where you just can't hop off.
So you're going to, well, I guess the example that I gave last week is if you, so for breakouts, it needs to first learn to press fire at the start of the game. And if it doesn't do that, then it just doesn't get any reward. So at some point it learns to press fire. And what you see happening is that it just keeps pressing fire because it learned that was something that gave a reward before. And if you're overfitting, so you're basically just, you keep pressing fire.
I must admit that is, I think, what I did as a kid, that I thought every time it hits the board, you have to press fire to push it off. So yeah, I guess I'm just another reinforcement learning algorithm.
So I guess another way of looking at this, I think, is that policy gradients have to be sort of on policy. So that's
wait.
different.
So the on policy method reduces that variance again as well?
No, that's the so. The fact that you have to always observe the gradients at the point where the policy is right now, because otherwise it doesn't make any sense. You can move away from it slightly, but not too far. And that is also a source for high variance. It's basically,
so instead of, you could have kind of like a slower learner, but not a behavioral policy. There could sort of be like a retarded sort of learning function to make it learn more slowly. But you wouldn't.
So that sort of slowing down of the learning, that's precisely what this PPO and TRPO is. It's precisely that. Right.
I don't know if anyone's seen Breakout and actually saw how the algorithm works in terms to get the optimal policy, but it actually found a very novel way to actually win the game, which was actually to shoot and for the ball to actually go up at the top and just hit the top and just go up around the top quadrant, which is obviously cheating. But I mean, if
no,
you
it's not.
But
don't be a scrub.
But if you actually saw it, I thought it was quite interesting how the game itself taught people what the optimal policy was to find. So
cool. Okay.
The last part of the question, what can we do about it?
Oh yeah. Sorry. Yes.
So I get.
Train more.
You can make sure that you don't update too much. So that's what the new algorithms are basically doing.
I think the correlation with the PBO algorithm as well.
Oh, is there a way that you could use some kind of state space annealing kind of thing, where you basically?
What is state space annealing?
I just made that up. But so for example, if I noticed this, and I know this is an example from like old school sort of frozen lakes and things and whatnot. But a lot of the things that I saw happening in the very first, when you had like a randomly initialized queue table and so on, was that your agent would bump into walls all the time and things like that, and or just would run in circles and whatnot. So I would imagine one of the things that you could do there is you could just kick it, right? And you could just teleport it to another area of your state space.
Yeah, that's kind of what you do with experience replay. That's
Exactly,
the cool thing.
right.
Yeah.
So, but that doesn't work with policy gradients,
Yeah,
right?
yeah,
So
good
could
point.
you though? Could you, so to speak, force your agent into another area of your state space if it's similar to what Dyna Plus does or Dyna Q? Can't remember, where it has this sort of opposite growing function where it says like it has this kind of memory of where it's been, and if it neglects an area of the state space, it just grows this desire to go there again. Is that, would that be useful?
I don't know how you would do it. I don't know. I don't have.
The short answer, yeah, it would be useful, but to actually the algorithm to do it, I think you were touching upon two algorithms there, the Rich Sutton one as well as Chris Watkins one, the combination. So that was probably already addressed there, but I do need to check that.
Is that because one of the things about policy gradients is that we use it when the state space gets like continuous or like incredibly large, and I would wonder how much you would need to know about the state space to change the sort of to teleport your agent through the state space.
It's very interesting,
Yeah.
actually. I really like it. It's basically experience replay, but you do the replay as new starting point.
Yeah, exactly.
Very interesting. I'm not sure. I don't think people have done that. No.
But isn't this asynchronous actor critic working to that effect when we have like a multiple threads with different poses?
What? Sorry, I didn't. What?
Yeah.
Yes, I think I want to say this. I wanted to ask actually if this asynchronous actor critic worked to that the same effect, where there are multiple threads with different policies.
Oh.
Yes.
And then it would like sort of randomly pick between all of them to reduce the variance, because that way it's not just. I thought so. Oh, and I was going to say just before I passed it up. Anyway, I'll remember later.
So is that similar to swarming? Is that similar to swarm? What's that called? Oh God. I think it's a subsection of the evolutionary algorithms where you have swarm.
I know what you're trying to think of. There's two things here. Yes, to answer the question. So advantage actor critic have multiple threads, and it looks at the optimal thread, and then actually. Yeah, and picks from that. And I think there's the swarm one, which I know what you're talking about. Sorry, I can't remember.
I think it's an evolutionary algorithm, swarm optimization or something.
Yeah.
I don't remember the exact name.
Well, I think it's an old one. It's an old algorithm. And it like 90s, but it was one of those things that didn't have like with anything computational to actually achieve what it needed to achieve.
What was the difference between A2C and A3C? I keep forgetting.
I'm not actually sure if there is a AC, then A2C, then A3C. I think they just called it A3C because it was asynchronous advantage actor critic.
One's
Yeah.
asynchronous, one's suspension.
Yeah.
One has like one extra feature to it, but they found it wasn't that.
That was
No, you didn't.
So A3C was pretty much like A2C. Is that what they were saying? But was A3C the one where they have the multiple agents, or is that still an A2C?
Yes.
No, so that's A3C definitely.
A3C,
Yeah.
and then
Yeah.
in A2C they realized it wasn't much of an advantage to have
Yeah.
the multiple agents.
So they just do add step bootstrapping there. Yeah.
Yeah.
I think so. The difference between A3C and using some sort of experience replay to kind of have a new starting point or something.
I think there was one where you start from the end point and you work back. That way
Well, that's kind of what happens in Monte Carlo, is that you just wait till the end of the episode and then you just kind of unroll the whole episode the other way.
But
But- But now it's so it's different. But so if in A3C you still all of your agents still end up at some point somewhere from the starting point. But if you particularly want like one starting point that you think is more important, like for instance in the sort of prioritized experience replay setting, then actually that might be a good idea to try. I haven't seen that.
Could you maybe pick? I wonder. Is there a way that you could maybe somehow not fragment? What's the word? Segment the state space, and then make sure that you have at least as many episodes, I guess,
Well,
or at least as you have state space segments or something like that.
So in experience replay, there is a way to prioritize which transitions are more sort of useful to look at, and it's typically the size of the TD error as you observe it. But I think it's a bit more. I don't know the details of that. I have to actually look into it. But yeah, there is a way to prioritize.
So like observe the change and then explore where there's more change.
Yeah. So the amount by which you learn.
Yeah.
Basically.
Is that kind of like is it almost like meta RL when you have a part of your algorithm that looks at how much you learn? That's because it's not just the reward, right? It's the next element.
The
so
level
the
of
TD error.
surprise.
Exactly. Yeah. Surprise. Yeah.
Yeah. I mean, I've heard a lot of words, and I could probably wave my hands a bit, but I wouldn't be able to actually make something.
We're physicists.
Say something sensible.
But what you say, effective saying is random. It's stochasticity. That's effectively what you're saying, and that's kind of built in.
Yeah. So all right. This is the somewhat. This is the part where we're getting to the not so incredibly serious.
Well, no, not really, right?
Yeah, that's a more or less. Yeah, that's a more or less straightforward.
Well, so I think so. In one of these interviews with this guy from the what is that famous robotics lab?
Oh, Boston Dynamics.
Yeah. So he's like, yes. They were like, how much RL do you do? It's like, basically none.
Yeah.
What, really?
The RL can use.
Yeah. I think they are now, but apparently it's not as crucial as for it.
I think we could have answered the one before because you kind of almost touched it. I think you can reduce the variance possibly by having a good attaching a tree policy on top of it that knows which one to select and knows how it can reduce the variance. I'm using an exploitation sort of algorithm, so that way you can get to the confidence that you want sooner in the right direction.
Well, you can truncate. What they do is truncate the MCTX. So they truncate the Monte Carlo tree search, so that it does actually find the optimal a lot quicker. In terms of this is actually a really fascinating question because this goes back to the early 50s and early 60s when they were designing robots and everything was designed with everything was handcrafted with expert features. And you look at what Boston Dynamics do, and it's wonderful, these expert handcrafted features. And I guess...
And they're so loud.
Sorry?
They're so loud.
Yeah.
I'm always disappointed. I want my robots to be like electric cars and just catch me by surprise.
I know,
but
you want it to
those
be
robots?
Whisper quiet. That's kind of what you want. But the key distinction...
That's the next question, hang on.
Well, perhaps what we heard earlier was, I don't know, them about to take over the world with that noise. It wasn't the air conditioning after all. They start with the air conditioning.
That's the first one.
That's the first rule, start with air conditioning and you can take over the world. But the key distinction, I guess, with reinforcement learning and what they're trying to achieve with, I guess, reinforcement learning is to take all that expert, handcrafted knowledge out, and so that's true reinforcement learning. That you actually don't need that, and you need to trust the algorithm to actually find the optimal policy. And I believe where they're heading with robotics now is a combination of DDPG as well as hindsight experience replay.
Do you reckon that's because it's so expensive? As in, getting a simulator for your robot, if it's just walking, that's one thing, but they do really sophisticated things now. Yeah. And do you reckon it's so expensive to get a simulator that does that? Or back then when they started, because Boston Dynamics has been around for a while.
That's a really good question. And I've thought about another algorithm there, which is going to become very popular, which is temporal difference explore, TD Explore. And the author on that was Todd Hester. And he wrote a really good paper in 2013, which will become very popular very shortly. And in terms, back to the question, the reasoning why they're, why they're doing this is that they wanted to train everything on games first because it didn't have moving parts, it didn't have the robotics component to it, which actually breaks. And if you find that if you're dealing with robotics, you spend most of your time trying to fix something that's broken rather than working on an algorithm to actually do what you want it to do. And I think they've got to a stage where they've got the preliminaries out of the way. That is, they've got an understanding of how a good reinforcement learning algorithm works, which now can actually be applied to robotics. And
Patrick?
I was just going to say, one of the problems with doing it in simulation is that it's impossible to build a good enough simulator for the real world, just because the contact forces and everything in the dynamics are just not quite right. So when you put it in the real world, it's just something's different. But what they've had some success with is called domain randomization, where they basically just randomize parameters of the simulation. So, colors are different, contact forces are different, and then they train in the randomized environment. So that when they take the robot into the real world is just another random environment that the robot has to interact with.
Interesting.
I think OpenAI's Dexterity robot was trained like that.
So, when they do that, what is the difficult part? Is the difficult part the environment itself, or is the difficult part to simulate the feedback that the robot gets?
There's a couple of things. The state space and the action space is huge. It's continuous, and if you think of something like a hand, like how many degrees of freedom you have, and then if you're interacting with different types of objects, different types of materials, and different orientations, it just blows up massively. But the randomization seems to work well.
Yeah.
that reminds me of the first robot that was developing in Japan. I think it had 23 degrees of freedom, and this was in the early 80s. When they were, sorry, it's off the cuff. I can't quite remember the details to be really precise, but I know that the first robot they were trying to build in Japan before Asimov, before the latest one that came through, started off with 23 degrees of freedom or something like that, which is but
Cool. So it's but in the end at the end of the day, it means that it's expensive. You just have to rebuild another universe and train it there, and then you'd be sorted. Speaking of universe, and that's the question that I'm going to open my beer with. Right. So people keep talking about sort of whenever you see reinforcement learning mentioned in the media, it's usually with a picture of a Terminator. I just one Terminator. Is this the thing that's going to kill us? Is this the thing that we have to be afraid of, or is it another type of AI? Is it another type of deep learning? Is this even the road to anything like that? Is anything that Kurzweil or Stuart Russell or Yudkowsky are worried about? Is this kind of behavioral mechanics or behavioral learning the sort of thing that they're afraid of, or is it something else?
It's interesting because there's a lot of books out there at the moment in terms of what's got to effectively take over the world. I actually think it's more to do with a misunderstanding of artificial intelligence. I think generally speaking, with the people who are leaders in the field, who are looking at ways, they're generally trying to look at ways for the betterment of humankind, and I actually really do believe that. In terms of I don't think anything's going to overtake the world. I think it's got to complement scientific fields, and I think it's going to complement areas that are going to be helpful to humankind. Because I think the biggest thing we're going to be looking at very shortly, or even now, is ethics in artificial intelligence, ensuring that is the case. And that's the personal viewpoint.
With that, just to hook in there, I've got two questions coming from that. One being with what would you guys think is the difference between actual ethics and these reinforcement learning algorithms that I at least remember seeing on archive of papers being written about that are trying to find their own reward function? Is that the same thing? And the other being, if you haven't had a chance to listen to it yet, I can't remember whether it's the most recent one or the one before last, Sam Harris's conversation with George Dyson, Freeman Dyson, and oh god, I forgot her name. Freeman Dyson's son. Yeah, but everyone always only.
Stuart Russell.
Yeah, exactly. And then Alison Gopnik. Yeah, But everyone always mentions his dad, whereas he in his own podcast, or like it's in this podcast, it was more his mum that influenced him in his career. But he makes this interesting observation where he says, to him it appears more like he was not so much afraid or cautious or nervous about artificial intelligence. He is more worried about natural stupidity, because it was his observation that he felt like he lost a lot of personal sort of human skill and intelligence when he got too used to using modern tools. And he felt like his time that he spends in, I can't remember what he was, he kayaks a lot, and he spends a lot of time sort of in the wild and on his own, and he feels like that gives him a lot more use. It must, I guess, must involve some brain functions that we otherwise don't often employ. And I wonder how much we are sort of stepping out of the way the more we're using this sort of thing. Yeah, if I had a pamper robot that treated me like, you know, the prince in Coming to America all day long, yeah, would I even be thinking about what I want and what I need anymore? And would we lose that? Are we maybe not? Is RL really going to take over the world, or are we going to give up the world? Maybe, yeah.
I've got a fairly strong viewpoints on this. My response is no, because if you think back through the ages, and you think back through the Renaissance period, where you think of the great thinkers, they were always thinking about doing something better, always thinking about coming up with ways how to do things, and more often than not, they were taken care of. You know, they didn't have to worry about financial matters. They didn't worry about, you know, food, because it was all, you know, just basic comforts. But they were allowed to think and think of ways. And then going back to the point, will we become, I guess, effectively slaves to these AI, which would then dumb us down, which is kind of what you're saying.
No, I don't think so. I don't think they would, because that's
because I'm saying it's not. I'm saying it's the converse of that. It won't dumb you down.
Like they would be breeding us dumb or something.
Yeah.
I don't think that's necessarily the case. Because what if? Because one of the things that these thinkers, and like Descartes, for example, was one of those that they had to earn money. Like Michelangelo, the reason that the paintings on the ceiling is that, you know, man has to eat, and so he was a good painter, so the church paid him lots of money. That's of course, but the thing is that if we get, let's say we get an AGI, just sort of, you know, imagine we make that work. I don't have to think anymore. That thing's smarter than I. Right?
Yeah.
And it grows faster. So I don't have to, none of that thinking. I can outsource all of that, and it'll have a better idea than me anyway.
No.
And it'll probably become a better writer and a better painter, and it can just read my thoughts. And the symphony that I had in my head, I just basically I fart and it's there. And it, you know, why would it still need me? And I can just sort of chill on the beach. Interesting in a similar way, I suppose. The Robin Hansen's idea of the emulated people, the Age of M, I think, is his book. That's a not quite as bad, but a similar kind of thing where he envisions these emulated people that are really, really efficient and really good at working, and they take up all the computing power and they generate all of this wealth. So the rest of us don't actually need to work, and we just can lounge about on the beach because there's just so much wealth going around that no one has to suffer, no one has to hunger.
Well, it's interesting because there's two things there. I mean, if we take the Michelangelo analogy a bit further, my understanding was he was a sculptor first before he became a painter, and that's what his profession was. So let's say that he could program an AI to do sculpting for him on his behalf. Let's say he can do that. Well, he's got his Michelangelo sculpting going ahead whilst he goes and paints his Sistine Chapel. You know, or the converse, or vice versa. Now, what you ended with, there was an interesting thing about the Brazilian thong salesman, or we call them flip-flop salesman, in that he spends most of his time on the beach, and he sells his thongs or flip-flops, or depending on what country you're from. And then a marketing guy comes in, a sales guy comes along and says, you've got a great product here. What we can do is we can franchise this. We can open up all these stores here, and we can get some more revenue coming through, and you get more money. And with more money, you can buy, you can employ more people, and then by employing more people, you can get a bigger house and all that sort of stuff.
Yeah.
And then it's just like, wouldn't that be great? And he turns around and go, well, what do I do then? Well, you've got all this free time to sit on the beach and do whatever you want. He goes, well, I already do that. Because he sells everything, because he lives within his means. I guess that's probably the point. And with this, I really believe it's going to complement a lot of professions. I think it's going to allow people to achieve wonderful things, and that's kind of what I believe. And that's weapons is a different story. That's actually quite scary, very scary. But yeah, I'll pass it on to someone.
What I think he's saying though is that you'll go further than that. Like it'll go further. Like it'll allow you to do things, but he's saying like you'll live and do those things as well better than you, like regardless. Yeah. So it's like there's really nothing. But then I guess if you want to chill on the beach, that's fine. Yeah.
Interesting thing that we've done recently is because we have Hello World, Hello OpenAI. We have played with the GPT-2 mini model, yeah, and we'll make our way to the larger one someday. But we fed it plays from Shakespeare, and it came up with this quasi-Shakespeare stuff, yeah, which was cute. But we fed it Beckett because I like Samuel Beckett, and it came up with rubbish. Like it wasn't even close, yeah. So there's this interesting thing where I wonder whether it'll take a while to catch up with us, or whether there are things that are so. Maybe they are, and that's another thing that George does. His comment was that he reckons nature uses so many non-algorithmic ways of control that maybe a lot of these things are non-algorithmic and therefore a little less easy to produce with the means that we have. Yeah, and so things like poetry, things like art might actually be a bit further away, especially when it's something that is strongly emotional and strongly abstract like that, or strongly, I guess, weird, kinky maybe. I'm not sure how to call it. And it would be interesting if that drives us in two directions. We become sort of where we won't get many more War and Peace or many more Lord of the Rings or many more Game of Thrones like works, but maybe there'll be sort of another niche that opens up for us. There'll be sort of an evolution in terms of we evolve into a species that does art or does music in a way that sort of is special. So I guess similar to I was talking to someone about this recently about baristas, that there are two markets I would imagine for, like, there will probably be the machines are getting better. They're definitely getting really, really good at making coffee, but anyone I talk to about coffee says that the person making the coffee is really the influencing factor when it comes to the flavor and all of that. Like you see this in the milk. Like I drink mostly soy, and you can see when the barista really knows what they're doing, because the milk will look completely different. Like sometimes you have this weird, different sized bubble kind of mess, and sometimes you have latte art in soy milk, and it's just wow, yeah. So, and it seems to be a lot harder with soy milk. So maybe there is a market for these machines for someone who just wants to run into a 7-Eleven and get a cheap coffee really quick, and someone who is like totally into this and loves exploring coffees and going to their personal barista, almost like artist, I guess.
I think it depends on time frame. Like if we go like medium distance, then yeah. But if we're going like infinite, then they'll probably have solved everything, right? I mean, potentially, depending on resources and everything.
I hope that infinite is before the heat death of the universe, then, because that's a.
If you go to San Francisco, you go to Seattle, you can serve a robot will serve you coffee. You can do that now.
But is it as good as coffee in Melbourne?
That's a different story. Will it be as good as somebody who prepares your coffee with love? Probably not. But also, a lot of if you get a good barista, more often than not, it's a conversation as well, and that's really important.
Because Go, for example, it created new ways of playing that even humans hadn't thought of. So it's actually more creative, more interesting than humans. And I think eventually with baristas and everything, they'll get better and more creative, and they'll be on point all the time. Whereas a human can be bad, good, but they'll be at the top, like,
the thing is,
all the time.
it'll come back to the optimal get it
All right.
to, so
Cheers.
it has-
See you next week. So maybe in like 50, 60 years we will have AI trainers, and it won't be Mr. Miyagi that tells you to wax on, wax off. It will be like a computer-generated voice that says, "Yes, but have you tried catching it while you were standing on your hands?" And you go, "Oh my God, I would have never thought of that."
I think it was personal.
So yeah.
But I found it interesting that you trained GD.
Thanks, Patrick. See ya.
With Samuel Beckett, and it didn't actually come out as well as Shakespeare.
It wasn't even close. It made. The interesting thing is that with Beckett, it often makes no sense, but you feel like it has a sense. But with the sentences that thing generated, it made zero sense. It was just completely random. Yeah. Very interesting.
Because the volume of works to train it, that could be something. I don't know.
True. Yeah. Interesting whether, yeah.
But in terms of music, I think they got handled Chopin, the using Musenet, and that's actually came out quite well. If you actually look something recently. So when it comes to music, I think AI is going to produce outstanding music. Like now onwards, that we'll see a chart, a number one, probably this time next year, and I'm not even joking about that. I really think they'll see it number one this time next year, just on music, with the lyrics, somebody then throwing lyrics on top of the music. And I think they'll get somebody who's already like Elton John, somebody who actually knows how to, do a performance.
Oh, you know what would be cool? Like you could bring, deceased singers using AI and then make.
They already do. Yeah, there's already AI musicians out there.
That's going to be huge business.
That'd be, some of that anyway.
I think my favorite would be if you had a band and you like Dream Theater is one of those cases for me. I don't really like any of the albums after the Awake album, and they're great musicians. I have nothing against their art, and they can do for crying out loud. They don't have to cater to me. They can do whatever they want. But if I could feed my machine those first 3 albums and then just make me 3 more, please, that would be great. Yeah. And that sort of thing, that throws up a really interesting questions in terms of copyright, for example. Yeah. Those 3 new albums, are they my idea if I program the network, or is it all based on their creation and therefore, but what if I make music and listened to their stuff? Is that the same thing? And it's, yeah.
Not making money off it.
Yeah. So
I
it's,
think it goes back to the original.
But because if there's no profit, it's just for yourself. I think it doesn't matter as much as what I'm saying. But if you're making money and it's their voice, then probably there will be
But
some.
what about DJs? And then it goes back to like DJs sampling music. And I think that is the 8-second rule. If it's anything, you can sample up to 8 seconds. Anything more than that, you can't. It's legally bad.
Yeah, I'm not sure because I guess they're playing it in front of people. But if it's for yourself, I'm not sure.
yeah.
If it's for yourself, that's private.
Yeah.
That's
So and what's the difference basically between a copy and between a, I guess, newly generated piece of music based on your favorite artists, or even different? let's say you had this case where you'd say, okay, here's where the 8-second rule applies because you only used, let's say Elton John dies. So I hope not, but Elton, sorry, but.
just for
Yeah, just for.
I thought he's still alive. Is he? I don't know.
Yes, he is. He's still standing. Actually, Bowie's a better example because he is missed just as much as Elton would be. So, but let's say people wanted to go and make more Bowie albums, and because there's a huge body of work there, so you could feed this algorithm a lot of material. Yeah, and people are doing this as a homage already. Like you find these amazing artists on YouTube which do covers of, I don't know, like you find covers of The Lion King in like David Bowie style and stuff like that, right? So, and then you'd have just a,
Sorry, that's on
it's look for, I can't remember, it's this, I think it's an American or South American a singer, and he does these amazing videos where he does like 20 different styles in 1 minute and stuff like that. It's fantastic.
Amazon did that, right? They can make anyone say anything as long as they have enough of their voice. They can make them say.
Yeah,
anything.
that's a lot creepier, I think. But anyway, but what I meant was you then make a new song in this style, like completely with like voice and everything. Yeah. And so I would imagine that Bowie's estate or his record company or something would say, hey, you're making money off what we produce, what we made money of originally. And then, but if you're a fan, if you're not covering, but if you're listening to a lot of Bowie all your life, yeah, and you learn to play an instrument, and people say, "Wow, he's great. He sounds just like Bowie." That would certainly be okay, right? So we isn't this distinction a little artificial then? If you did that,
that's different. So
yeah,
what I guess you raise a very interesting point there, because you sample your favourite artists, or their lyrics, or their music, produce something which is palatable, and then re-record it yourself as your own individual work.
yeah.
Yeah,
So have you
look,
seen the
honestly,
Google
I reckon
Doodle?
that would happen, because if you actually see a lot of artists now, a lot of people go, they sound like so and so.
Yeah.
Even with early Oasis stuff, didn't that song kind of sound a bit Beatles? Like, you know, now it's like people would sample Oasis stuff, mix it with the Beatles stuff, and go, hey, well, now I've got a new sound.
Mm.
And I'm just feeding through an AI, which is, instead of me actually mucking around with it, an AI, I can produce it in a day, saves me like 6 months of studio time.
And that was the Google Doodle, right? The Google Doodle on Bach's 300th birthday or something. The Google Doodle was saying, or was like taking a melody that you had made, like with 2 bars, like nothing fancy, and harmonizing it in the style of Bach. And it sounded pretty good. Like it was like it made something that sounded Baroque with pretty much anything that you fed into it. And you could like have interesting scales, and it would still make it, it would still solve it usefully. And so I guess you could approach it like halfway, right? Because if you had an AI trained like that, and you say, oh, okay, what's a Ring Around the Rosie is a very popular, I guess, very well-known song, and you take that, and then you just have your say my Dream Theater trained algorithm, and it says Ring Around the Rosie with like distorted guitars and drums and everything. Okay, well, whose copyright is this? Like, is this?
But then change the lyrics.
But yeah, that too.
That's the smarts to it.
Yeah,
it would be, it's like take something, a formula that they know works.
Yeah, exactly.
Keep it to 3 minutes, which is usually 3:30 minutes. That sort of thing. But then you just change the lyrics to something a bit different. Re-record it as your own and pass it off as your own work. And the AI has done all the hard work for you. Because it's already done on the set. It's done 3 years of sampling in a week, effectively.
Yeah, and there's, as far as I remember, there's an AI-generated script for an ad out there as well. Like it was a car ad, I think, that was written, where the script was written by an AI. Yeah. So interesting.
Oh well, it's pretty. It's simple. It's like create a need, create a want, make you feel crap about yourself, and give you a solution, and then that's kind of the script.
And then it was literally like it had as far as I remember, it had given like stage instructions and so on as well. Like there was which kind of what the shots were to be used for the car, and what the flow was of the ad, and the color spectrum and so on. So it was interesting. It's very interesting. Yeah. If not, why not? Well,
we've kind of said yes.
Yeah.
It
depends on how you find technology.
Yeah, fair enough.
Are we going to become slaves to the when the robots are taking over?
Yeah.
Was it like the Rick and Morty episode with the dogs taking over the world?
Yeah.
Yeah, I think like I found the kind of this matrix concept like really ingenious.
I know. Are we a simulation? I wouldn't be surprised.
But this element of people being reduced just to the power source.
Yeah, but I mean,
As a physicist, I can tell you that's a shitty idea, because we're shit power cells. We're super inefficient. There's way better things to do.
Further, it's just like, is this a simulation now?
Yeah.
Because like, if that's already happened and time's not linear, surely you can just go back and pre-program everything.
I'm just wondering, because we create robots, right, and they take over and they whatever create simulation, but the robots can't really, can they go a level higher? Like if let's say the robots could create something that take over the robots, that's not really possible, is it?
I think the simulation argument is a more interesting and modern evolution of the God argument and the resulting answers because of this. To me, it feels like sort of a Gödelian problem. Like it's so outside our experience that we can't really get any information, so we can just make all sorts of assumptions, and then we would have to ask, okay, so who created that? Yeah, and because we are trying to answer a question that we have difficulty gathering data for, we're not really, like any solution that we provide wouldn't necessarily answer it, because it would still cast the same question again, I guess. Yeah.
It's like like a whole series, and then the producer dies. I mean, no one really knows like what he really meant by something,
and why does it end in a church?
This is how the game of
Everyone's like speculating, but no one really knows, like, you know.
Yeah.
What is it?
Apparently,
it's fun though.
Yeah.
It creates like.
If I understand this correctly, with Lost, one of the reasons was that they never thought they would actually pull this off, and they started writing kind of like Battlestar Galactica off the top of their heads halfway through, and they just came up with too many interesting ideas, and then never knew how to pull them together.
I saw like a great comment under one of the Game of Thrones videos, was like a comment, so that HBO to the script writers, what do we say to the good script writing? And the writers, not today.
It's maybe we should invite everyone who's still watching, haha, now that we're talking about Game of Thrones and Lost and other things, to just join us at the next Reinforcement Learning Book Club, because it gets really interesting once the reinforcement learning questions are over. So
I just want to look at those of Fred's touch, but I think the argument to looking at the past and the great minds and inventors of the past is that actually, I think in their times, the conquer and the taking over the world wasn't an option. As I think they were selfless in a sense, that because that wasn't an option. And I think today it is an option. So maybe that's why they think it was directed towards the benefit of all.
But I also think it's the benefit of why. I think why it's like why things, why does this happen? Why does this occur? Those sorts of things. People always trying to answer that question.
Yeah.
And constantly asking why, not being satisfied with the answer you get, and actually trying to work out a better way to do it, or actually work out the solution. And even now, I think there's that natural competitiveness, which is healthy.
Yeah.
I actually think it's quite healthy competitiveness now in this sort of area.
Yeah, I think it's what is Darwinism. I think everything can be tracked down to Darwinism, but yes.
Interesting. So it could just be simulations from other humans trying to figure out like whether something works or not. That's interesting.
I think there's
but it's like, oh, sorry, go ahead.
I think you mentioned this human factor and this factor of unpredictability of the humans, their behavior. But I think if you think like with the machine's behavior, there could be like certain distribution, and there will be those layers of unpredictability, or what we call the human behavior, the unexpected behavior, and they just act in the same way from time to time, and that can simulate human. So I think the human factor is overrated. And I think that
I have this image of these this sort of story of like two warring AIs, and one of them is Alpha, and one of them is Omega, and the one that really messes everything up is this tiny AI called Epsilon. That is still exploring.
I was thinking, because if we in the future, when we come up to face problems, we're like, well, we can just simulate it now, and then but for that simulation, they have to be very human-like, and so it's like what Elon Musk was saying, like the odds of us being not the simulation is so
yeah, that was very interesting. But at the same time, I was coming back to like how real is real, right? And I'm kind of jealous. I'm kind of jealous of if Patrick's argument sort of continues, and if this is not really real, if this is just sort of an approximation, then I would really like to have sex in their space, because sex is pretty fun, and wow, theirs must be awesome. And so, like, if this is an approximation, I wonder if you could sort of draw kind of these kinds of conclusions there, or if this is not a simulation, or maybe at the same time, maybe this is just such a limited space. Maybe, you know, they're just sending us some weird signals from outer space, and that's why there's no life out there. They're just simulating this one. Maybe they're simulating another planet with life on it in their densely populated universe in another computer, and that's why there's.
If you take that
Yeah.
further, what is it based on? It's based on neurology. It's based on neuroscience.
You mean the approximation?
All
The-
our perceptions based on that.
Yeah. Oh, you mean like the Cartesian demon? Like it could be just I who is simulated, and this is all.
That's it, and it's stimulation. So if
Yeah.
you broke down all your senses, I think 30% vision or something like that, and then you break it down further, you go, well, whereabouts from a neuroscience perspective is the most important component of the brain. And I think the hippocampus, but I think that's the most important one. That gives you that stimulation.
Yeah.
And so if it could be we're just heads in a jar somewhere.
Yeah. Boltzmann brains.
And just plugged in. I mean,
Yeah.
how
One more comment is that you mentioned all the software applications that help us. I think now we can say that there are haves and haves not, and I think maybe in the future there will be like a dumps and not. So there will be like people that create those things, and there will be people that just use those things.
I think it's going to be more of a case. Well, I hope so. I hope not. I think it's going to be a case of if you were going to look at segments of society, I think the most important thing is obviously waste management. That's the first thing. Second thing is water purification. And third thing, having good infrastructure in place. And the fourth thing is education. And if you pull these resources together and we take an area such as Africa, we pull them all together and we can address those four issues, that people can become better educated. And I think if you become better educated, you effectively become self-sufficient. I think that's what they're kind of trying
Oh,
to draw.
this is a brilliant. Sorry, that didn't mean to be a spoil sport, but my laptop is just now going to run out of juice, so I'm just going to officially declare the. Oh, it's already there. Oh, see, damn it. See, and I'm just going to declare the official part over, and thank you for watching. See, perfect timing. Yes, thank you all for participating, and I think the last, 10-15 minutes of this was sort of like a taster of what we have already been talking about at ELISA to do as a proper podcast. Just get a six-pack, put a six-pack on the table, get a handful of people together, and talk about this sort of thing. Like, oh, wait a minute, if that's true, what if, yeah? And so these kinds of explorations will make for a really interesting podcast.
Yeah,
So thank you for watching, and I hope to see you next time.